And just like with melatonin secretion, how it is cyclically released at night when there's a lack of light entering in through the eyes, through the retinohypothalamic tract, the SDN operates much the same way, where it's able to maintain that rhythmicity utilizing the input of light and darkness as well. They've done studies on the SDN where they have, if somebody had a lesion or some type of defect with their SDN, they've done transplants of the SDN. And what they found is that the person that had the donor SCN, their sleep wake cycle took on that instead of the brain and this new kind of implant that they had taking on the cycle of what they had. Instead, the person adapted and revised their sleep wake cycle to that of whoever the donor SCN was. They've also done dissections where they've taken apart this area of the brain and they found that every individual cell of the SCN all operates on this 24-hour rhythmicity. But what happens when they come apart is they all start to kind of, although they're all operating on their own on 24-hour rhythmicity, they start to become out of sync with each other. And so they're all operating on a 24-hour cycle, but they're not in the same synchronization. And so what that really showed was that the SCN helps to keep the brain and all the bodily rhythms within the same stage or the same, it keeps them all synchronized together. So they're all on the same page in terms of whether we're awake, whether the brain's asleep, whatever stage it's going to be in. The cerebrum is the largest portion of the brain. If you were to just look at it, it's got a lot of convoluted, folded layers of gray matter that really cover the outside of it. And half of it is actually hidden within the folds of the wall. So the folds are called sulci. And the reason why that you have all this folding and all that is to increase the surface area of the brain, to increase how many neurons are available. There is two separate cerebrums, the left and the left hemisphere, the right hemisphere, and they are divided by the longitudinal fissure. What connects the left brain and the right brain is a band of neurons called the corpus callosum, and that's how the two left side and right side are connected. There are certain surgeries that would actually disconnect the communication between the left side and the right side. It's a surgery done. One of them reasons why somebody might have that done is if they have severe epilepsy, where if a seizure were to start on one side and then progress to the other side, if they weren't able to get the seizures under control, in severe cases, what they might do is sever the communication between the two sides. So that way, if a seizure were to start on one side, it wouldn't progress to the other. And you can still live and function and do be a person without your two hemispheres communicating to each other. It just has some interesting side effects. The cerebrum has a lot of folds, the gyri and the grooves, which are the sulci, which significantly increase the surface area of the cortex so that millions more neurons are permissible within a single brain. The gray matter is located on the outer surface, and then we have these different, this is where, the area of the brain where everything is felt and perceived. We have the sensory area where our sensations are actually felt. And what you'll find is the area on the brain of where the sensations are actually felt is correlates not to the size of the body part, but rather the number of touch receptors that are in that particular body part. So a good depiction of this is it's called a homunculus, which is a representation of the anatomical divisions of the motor cortex and the sensory cortex, our motor strip and our sensory strip. It's a whole strip where everything is felt, and this is the strip where all of our movement is initiated. So what you'll see is that, like, on our lips and on our hands, there's a lot of real estate that is dedicated to these parts of our body because there's a lot of sensory neurons located within our skin there versus, you've come up here, you got your elbow, and your whole entire leg has a pretty small area, even though it's a relatively large part of our body. We just don't have nearly as many sensory neurons there. And kind of the same thing in thought process here on the motor strip. We need a lot more dexterity in those minute movements of our hands versus, in our entire thigh and things like that. But a homunculus is a really neat kind of representation of where things are felt and where things are, or where movement is initiated on the cortex of the brain. The cerebrum is further divided into different lobes. It's really important, as in terms of sleep text, to know the different lobes and about where they're located, because this is all comes down to where we apply the electrodes for a sleep study or for an EEG. So the way the lobes are named is named for the skull bone that overlies that particular area. So you have the frontal lobe, which is pretty much the entire front half of your brain, and that's important for your motor function, for moods such as motivation, aggression, moods. So for instance, if you've ever seen or read the book One Flew Over the Cuckoo's Nest, it's a movie with, they made it into a movie with Jack Nicholson, but he had a lobotomy. There was another movie, I think it's Shutter Island. It was a book too. I read the book. That same thing, the person had a lobotomy, but I'm sure you might have heard of it or seen it in movies or whatever. But it's a procedure that used to be done in mental health facilities or in prisons on people that were aggressive or they're hard to control. And so basically what they would do is take like a pick and insert it through the eye socket and kind of scramble the front part of the brain. They'd scramble part of the frontal lobe. And what they would do is they would eliminate that area that had aggression. So these people were a lot more pliable and easy to kind of to use or to manipulate, and were more obedient. But what they would also do is, it's the same part of the brain, they would scramble this person's motivation and their voluntary motor function. And so these people would basically become shells of a person with no real mood or motivation or anything. They would almost become like living zombies. Thankfully, it's a procedure that is not done at all anymore, at least not in America and in a modern practice of medicine. The parietal lobe is right behind the frontal lobe here on the top upper half of the brain, on the upper half of the skull. And that's where we get most of our sensory information, except for smell, sight, and hearing. The temporal lobe, which is just above your ear, kind of along the side of your head here, is the area of the brain that receives a lot of our sense of smell and our sense of hearing. It's also important for memory. And the occipital lobe, which is in the back half of your brain, on the back of your skull, that's where we are able to really see. And that's where all of our sight input comes through. And it has the ability of neural plasticity, which means that it has the ability to adapt to our changing needs. Meaning like it can recruit those neurons for different functions. So you hear about people that are blind, their other senses are heightened. Well, that's true, because if this whole entire area of the brain isn't getting used for sensory, the sight input, then it's going to be used, they're utilized for other things. Because our brain is plastic. It can adapt to how and what we need it to be. The younger the person, the more plastic the brains, and brains of children are extraordinarily adaptable. So knowing the different lobes, you'll notice that when we learn how to apply the electrodes, they're all named for what area of the lobe that they're over, except for the central. The C3, C4, those electrodes are placed over the central sulcus, also known as the Rolandic fissure, and that's essentially that divide between your motor strip and your sensory strip. So it separates your frontal lobe from your parietal lobe. And it's that, you have a left and right hemisphere, and you also kind of have this strip or section divider right here that divides the frontal from the parietal, or the frontal and the back half. But that's also where, when we showed that homunculus, where these strips are, the sensory strip and the motor strip, that's where they are. They go side by side on each side of the brain, and it's what divides the frontal and the parietal lobes. Oh, that's what I just said. Another kind of depiction of where that central area is, or the central lobe, where we're applying those electrodes for the sleep study and for EEG, right there between the motor and the sensory cortex. So for an EEG, they're the electrodes that are placed on a person's scalp to record their electrical activity of the brain. It's not detecting single action potentials of a single neuron, but rather the simultaneous action potential of a large section of neurons over which that electrode is placed. So it's not sensitive enough to detect the individual action potentials, but it does pick up this constant electrical activity that is always being emitted from our brain. And then part of this course is learning how to read that electrical activity by looking at how fast it is, how intense it is, to really be able to determine what state of brain activity the patient is in, whether they're awake, whether they're asleep, and specifically what stage of sleep that they're in, all of that. This is an example of some of the electrodes being applied, way more than we would typically do in a sleep study or even an EEG. That's more for a research setting. But just to give you an idea, we can add a lot, especially for patients that might have abnormalities that we're trying to pinpoint to view. That's the beautiful thing about, applying the electrodes that we do, is we can always add more to be able to better see whatever it is that we're trying to see. So the resulting electrical activity that we see within a sleep study or on an EEG is this wave-like pattern, also known as the brain waves. And like I said, you'll be able to start reading these to determine the stage of sleep the person's in, whether they're having a normal kind of brainwave pattern or whether they're having this hyperactivity seen during a seizure. It's all part of learning the basics of neurodiagnostics. The cerebellum, or the little brain, functions below the level of conscious thought. It's involuntary. So it helps to regulate movement, coordination, muscle tone, posture, equilibrium. It utilizes info from gravity and the movement in our inner ears to help maintain posture and equilibrium. So big brain, little brain, cerebrum, cerebellum, I always used to get those two mixed up. And they're built the same way, in that, where you have all these folds and grooves of the cerebellum and the gray matter on the outside, white matter on the inside. The cerebellum is built much the same way, with the folds and grooves, gray matter on the outside, white matter on the inside. It's just remembering which one was which I always had difficulty with. And what worked for me was just remembering, cerebrum was the littler word, but it corresponded to the bigger brain. Cerebellum is the bigger word, but it corresponds to the littler brain. And I don't know, I was always able to keep it straight in my head that way, but I'm sure you might. If you come up with something better, let me know. The basal forebrain is an area in the brain. It's this kind of little pinpointed area, kind of towards the front in the frontal lobe. That is a focus for sleep research, and what they've found is it does play a direct role in cortical activation, so activating the cortex, waking the brain up, and also just maintaining homeostasis of sleep. So it is a really important part of the brain when we're talking about sleep specifically. What they found is that basal forebrain cholinergic neurons, so cholinergic as in I'm talking about, if we were to do autonomic nervous system, cholinergic meaning acetylcholine, they provide the primary source of acetylcholine to the brain, to the cerebral cortex. acetylcholine cholinergic. So just if you're struggling with the autonomic nervous system again and remembering the different subreceptors, go back to the pharmacology autonomic nervous system lecture, and I talk about, the subreceptors and what neurotransmitters specifically those subreceptors respond to. Well, the cholinergic receptors of your autonomic nervous system, think cholinergic acetylcholine. So it's in the basal forebrain that these cholinergic neurons really provide that primary source of acetylcholine, which we know acetylcholine is an excitatory neurotransmitter that's really important for not only wakefulness, but specifically REM sleep. And they are important for controlling this cortical activity and the different cortical activity seen and the different sleep and wake states. So it has a very important and critical role in activating our cortical EEG and providing that kind of that excitatory and fast EEG seen in wakefulness. The other thing that they've found in other studies that they found with the basal forebrain is it does help promote the recovery of non-REM sleep and non-REM delta activity after sleep loss. So when we talk about sleep deprivation, one of the things that we'll talk about is how when you are sleep deprived, sleep recovery is never linear. If you accumulate a sleep debt of 8 hours, you're never going to get that full 8 hours back. But instead, what happens is the architecture of your sleep changes to help your body recover somewhat from the sleep debt that was accumulated. And how it specifically recovers is by increasing slow wave sleep and REM sleep. So you'll find that somebody that is sleep deprived will have significantly increased amounts of slow wave or stage 3 sleep and REM sleep. And they found that it's the basal forebrain that was important in kind of that area of the brain that helps the body recover that non-REM slow wave or delta sleep after a sleep deprivation occurs. What we do know is that adenosine, a neurotransmitter associated with sleep, it's a chemical that accumulates in the body, that keeps accumulating in the body for every hour of wakefulness. And it keeps going up and up and up and up until eventually you're not able to fight sleep anymore, and you're able to, and you fall asleep. And what they found is this adenosine, because the basal forebrain it's more of an excitatory, it's important for the excitatory and increasing cortical activity. Adenosine inhibits the basal forebrain neurons because it's a inhibitory neurotransmitter. So it inhibits the cortical activating kind of sequence that happens within the basal forebrain. When they've done studies on patients that had lesions in this area, if they had a lesion in the basal forebrain, it caused insomnia. They were not able to sleep. With a large lesion found, it can cause complete sleeplessness where the person's not able to sleep at all, and it can be lethal. Lack of sleep, given it enough time without any bit of sleep or any recovery at all, it can be lethal within a few days. Smaller lesions, if it still caused a significant reduction in slow wave sleep by up to 3/4 or 73%. And the severity of the sleep suppression was significantly found to be related to the size and the localization of the lesion. So where specifically and how much of the basal forebrain was impacted by the lesion.